Welcome to CE 3305, and we're going to take the next topic relevant to open channel flow, and the last one is rapidly varied flow. The textbook does a nice job of describing rapidly varied flow, and it occurs in flow transitions when flow changes from supercritical to subcritical, over short distances. One common rapidly varied flow phenomenon is the hydraulic jump. Another one, of course, is the acceleration of flow going over a sharp edge where it passes from perhaps subcritical to critical and then to supercritical. Now, the hydraulic jump is a common rapidly varied flow phenomenon, and although we present it here almost as a novelty, it has some practical applications in energy dissipation, for erosion control, and although not commonly used, it's very effective at mixing chemicals. In a hydraulic jump, energy is not conserved. But usually, it's not conserved, so friction alone cannot explain the change in head loss. However, momentum is very nearly conserved. And in fact, we can use that principle to explain the behavior of rapidly varied flow. Okay, so let's consider just first a definitional sketch of a hydraulic jump. Let us assume that we have open channel flow occurring on a channel. In this case, it's drawn essentially flat, although the flatness is not a prerequisite for a hydraulic jump. In your laboratory class, when you take it, we'll use flat or pretty shallow slopes to generate the hydraulic jump, simply because it's easier to produce the phenomenon in such a situation. Okay, so there's our flat, and we have flow proceeding along supercritical, and then there's a very turbulent area indicated by my circular cloud, and perhaps flow continues onward, and there's our discharge diagram. So what's going on in this area is, if you recall our specific energy curve, what's happening here, at least conceptually, there's our energy, there's our depth, and it's on this line. This shallow stuff, we're down here, and so we're traversing this curve that way. And then at some point, pretty near or just past critical, the flow doesn't follow the line but actually jumps to a different step. I'm not going to show these as vertical because with the loss of energy it can't be, and there are equations to describe the approach depth and the exit depth, also called the alternate depth, and the sequent depth. And so let's just visualize two sections. Here's section 1. Here's section 2. And this distance is not particularly large. If you consider the previous numerical example where we had over 10 kilometers of distance for a 3-meter change in water surface and water depth. In the case of the hydraulic jump, instead of being in hundreds of meters, these distances are in a couple of meters, 2 or 3 meters. So these distances are pretty short. The tool for analyzing hydraulic jump is, of course, implied as a momentum balance. So let's go ahead and produce our control volume. Well, I'll go ahead and stick my favorite control volume color, which is green. So there's my control volume. It's supposed to just include the hydraulic jump. And if I was really anal, I would make the control volume follow that path, but I'm not that anal. So let's pull our control volume out and take a look at it. There's our coordinate system with the control volume, and if we remember back to our control volume lectures, we want to put the forces on the object. So we have Fp2, so that's the pressure force at P2, Fp1. We also have V1 entering, A1 looking out, A2 looking out, V2 looking out, and momentum for this case has that the sum of the forces is equal to d by dt, integral over the control volume, rho v dot d volume, plus the integral over the control surface of rho v dot dA. The way I've drawn it, my control volume is not deforming, so that part zeroes out. And so finally we have the sum of the forces, and we'll put the left pressure force, the right pressure force. There's the weight force, and we would certainly have friction. I may choose to eliminate friction or to neglect it because this distance is short. The frictional shear isn't going to be terribly huge. So on the left side, I have force, pressure 1, pushing to the right, minus the force at pressure 2, pushing to the left. And that equals the change in momentum, which is rho V2 squared A2 leaving minus rho V1 squared A1 entering. That can be expanded as rho V2 times V2 A2 minus rho V1 times V1 A1. That term and that term are both Q, the discharge in the channel. So the expression becomes force at pressure 1 minus the force at pressure 2 minus friction if we include it is equal to rho times V2 minus V1 times Q. And so that's just a straightforward energy balance. Momentum balance, excuse me. Now the pressure forces, force at pressure 1, if we look at section number 1, there's some water surface, and so we would typically assume hydrostatic distribution. So the average pressure is P1 bar, which would be basically rho gy, the depth, times a half, multiplied by the depth times, let's say, the width if it's a rectangular channel. So P bar 1 equals we'll call that y1 for the depth, rho g y1, and area would be y1 times the width. Again, we're pretending a rectangular channel. Therefore, force pressure 1 is P1 bar A1, which would be rho G Y1. It has to be over 2 times Y1 times the width. So 1/2 gamma Y1 squared width. Similarly for pressure 2, again making hydrostatic assumption that we're far enough away from the jump that that's an acceptable assumption. Force of pressure 2 is going to be gamma over 2 times y2 squared times the width. We can substitute those in. So gamma over 2 y1 squared minus gamma over 2 y2 squared equals rho v2 minus v1 times q. We could proceed forward to try to express y1 in terms of y2 or y2 in terms of y1. And for a rectangular channel, we would arrive at y2 is equal to y1 over 2 times the square root of 1 plus 8 times the Froude number at section 1 squared minus 1. This is basically the equation on page 579 of the textbook, and I've presented it here without a detailed analysis. We can apply this idea, and we'll use example 15. We'll use for an example problem 15.53. We'll use that as an example. In problem 15.53, we're presented with a channel, nice and horizontal. Told there's approach, a jump, and an exit. We're told that this change in depth, delta y, is equal to 14.4 feet. We're told the discharge in the channel is 65 cubic feet per second per unit width. And we want to know what is the value of y1. Well, we literally can apply the equation we just stated. We have the following. y1 plus delta y is equal to y1, the approach depth, or the alternate depth, over 2, times the square root of 1 plus 8 times the Froude number squared, minus 1. Recall that the Froude number squared is equal to q squared times top width divided by g area cubed. In our case, the top width in this problem is 1 because it's per unit width. Hence, the area is t times y, which equals y. And q is given as 65 feet cubed per second. So now we have 65 squared times y, 65 squared times 1 divided by g, which is 32.2, over 1 times y, which is y, quantity cubed. and that y is the approach y, y1. So now we return to the equation. Delta y plus y1 is equal to y1 over 2 times the square root of 1 plus 8 times 65, quantity squared, divided by 32.2 times y1 cubed minus 1. Do a little more algebra, and we have delta y is equal to y1 over 2 times the square root of 1 plus 8 times 65 squared divided by 32.2 times y1 cubed minus 1 minus y1. We simply put this into some function of y1, which we'll script in a second, and then by trial and error we can enter values of y1 until we get the correct value of delta y that was given in the problem statement. So let's go ahead and produce that script. So turn to our scripting tool. Let us clear the console. Create a new script file, mostly because it'll be easier to keep track of. And we'll call this the delta y is a function of y, A-P-P-R-O-A-C-H. We'll just use that construct. The only unknown is the approach depth. And now we can build the function. DELTA delta y is equal to, there's three quantities. Okay, there's the minus y1 term. That's the front term, and now the so the one that goes under the radical is 1 plus 8 times 65 squared divided by 32.2 times approach depth cubed. Closes off that one. Closes off that one. It looks like I have the syntax essentially correct. And we will return delta y. That's our function. We need to save it as the hydraulic jump. It's reporting some kind of syntax error, which has me a little bit confused. Let's jump over to times that thing. There we go. That's much better. I had a delimiter missing. Cool. Okay, so now we will use our delta y function, and we will start guessing. So what this is going to produce is the required value of delta y. Excuse me, it will produce the value of delta y that would be obtained from a particular approach depth. And we'll systematically guess until the value of y that we put in produces a change of 14. So if we put in 0.4, nothing will happen, because that's not where I need to do it. I need to do it down here in the console. Another syntax error. All right. So our first guess of 0.4, which I just simply pulled out of my datum, we would expect a delta y, a change in sequence depth from the alternate of 25, in this case feet. So that's too big, so we want to make our depth deeper. Let's try doubling it. 17, so we went in the right direction. Let's double it again. Now we're at 11, which is too small. So 1.6 is too deep. 0.8 is too small. So let's split the difference and use 1.2. 13.5, we're pretty close. We could split the difference again and go to 1.0. Too high of a jump. So now we know the correct value of depth is between 1.0 and 1.2. A logical one is to split the difference and go to 1.1. We're getting there, 14.34. We'll go a little bit bigger, 13.95. I'll split that increment in half, 14.14, 14.24. I went the wrong direction. 14.16, 14.17, 14.75, 14.54, okay, 1.1025. All right, we could continue on for a while. We have a nice answer around 14.4. 14.08 feet. So the approach depth of 1.1330 gives us about the correct answer. We could write a little Newton's method if we wanted to get this to get really a close answer, or the other trick is just do it by a graphic. I don't know, do 100 steps. I have a mistake. I need to make enough room. I think I got the syntax right. That'll make 100 replicates of that. Let's cheat. We'll do this as a sequence. No, we want to repeat 0 100 times. There. For I in 1 to 9100. Do what? We're going to delta, let's do a step size. So we want to start at 14.1. What are we going to do? This is going to be multi-line, so we have to force the line feed. We are going to compute DELTA. We're going to do current is DELTA y. It's equal to start plus SETP. Now let's just do it differently. Delta YY. I'm going to do this all up in a script. Okay, let's start everything. DELTA YY is repeat 0 100 times. Current is going to equal 14.1. Step is going to equal 0.001. For I in 1 to 100. Do what? We want to delta YY of I is equal to delta Y of current is equal to itself plus the step. And then we will plot one more term. I guess we'll get okay, so we'll take the current value, stick it to y value of I. This is going to be of I, and then we do an update. This is a pretty bad hack, but this should work. Save that real quick. Now we want to plot y value versus delta yy, and where it crosses over we can find the y value, and actually while we're at it I will print cbind of y value delta yy. Save, source that, and $14.199. Oh, it wouldn't kill us to do the right starting value. Our starting depth is 1.11. Let's try that one. And we are after 14.0. So if we look at our plot, 1.144 is pretty close to our best value. If we go back to our by hand stuff, we have 1.133. Let's try 1.144 just for grins. And that's it. So that would be how you would combine the scripting language and the analysis. Now obviously that was a fairly poor use of the scripting language if we were going to do this a lot. If we can do it over and over again, we'd put quite a bit of effort into structuring the computational algorithm to find results. One of the ways we could do that would be to program a Newton's method, which is described in the readings, and we can just nonlinear solve from that. All right, that concludes this lecture.